Morning. Welcome back. It's Monday. We're going to go over intermolecular forces today. I posted a warm-up on Google Classroom, so people are going in and answering those questions, submitting them. The first two will give you your answers right away. They are secured questions, so I won't be talking about those on video. The third question is presented on the screen in front of you, where we're differentiating between a small hydrocarbon. It looks very similar to methane, but instead of one of those hydrogens, we have a chlorine attached or bromine attached. And we're going to be looking at differences between these two and justifying the difference in boiling point. We're going to explain why the boiling point is different as a result of some of the given data, such as molar mass and dipole moment. So first of all, the types of forces that both of these exert, these are going to be, if we look at the Lewis structure, we have hydrogens attached and then focusing on the chlorine attached, and then hydrogens attached and with the bromine attached. And what we know is because the differences between chlorine and bromine, the electron cloud around the carbon-chlorine bond is going to be smaller than the electron cloud around the bromine-chlorine molecule because bromine is a larger atom. The dipole moment, the difference in polarity between them is we can say that the carbon-chlorine bond is more polar, but based on the data shown, the number as far as the values, they're really close in value. And as you get larger and larger in size, the dipole difference becomes less significant and the number of electrons becomes more significant. So they both exhibit London dispersion forces. They're both polar molecules, so there are dipoles. Those are the two forces present. But as we see, the more significant factor is how many electrons bromine has compared to chlorine, which affects London dispersion forces. So we can justify that the greater boiling point or the higher boiling point in the bromine molecule is due to the stronger London dispersion forces. And those London dispersion forces are a result of bromine being a larger atom, having more electrons, and a greater polarization of those electrons. So the answer that is presented here, the second bullet point, is the one provided by College Board. So you can take a look at that and compare it to the answers that you wrote. I can pull up some of the responses that we prepared as a class, those that were submitting their responses. And you can see that a lot of them are actually pretty similar, which is good. Here's some of the sample responses that we were getting. Just be careful that things like your answers support the data from the table. It is a higher boiling point as a result of London dispersion forces. So things like, since the electron cloud of CHBr is larger than CHCl, the LDS will be much stronger despite their weaker dipole. That is a really good statement right there. Talking about size and radius is good. We need to follow up with a statement of why that is significant. So hopefully you're seeing some sample responses and being able to adjust your current responses to add the extra level of detail to explain why the greater size is relevant, how does that connect to London dispersion forces, and ultimately make that connection between differences in boiling point. So there's practices here. I'm not grading this one. There's practices here to help you write your responses. You'll be typing them in on the AP test or writing them out and then submitting them. So this ongoing practice is going to be really important. Let's go back to our work for today. So a few weeks left. Hopefully you have been watching the YouTube links that are being put on Google Classroom, the ones that are being developed and released by College Board. Some of those are live videos. You can go and watch them live, or you can go back and watch them after they've already been recorded. I would say you should be watching one of those a day at this point. And then the weekly assignments for us are just practice with free response questions. And the office hours have been great. For some students have been coming in and asking questions. We've been having some good conversations on office hours. So even if you don't really have a question, people have been stopping by and for an hour and listening to the questions that other people have, and maybe it's sparking some interest and reminding you that there's still a lot of questions that you may not necessarily know what they are yet. With that in mind, there has been a lot of talk about intermolecular forces and how does that, and I wanted to get into that today. Focusing on types of intermolecular forces, how it relates to solids, and polarity, and then melting point and boiling point as a way of comparing strength. So here we go. First thing I wanted to point out is the difference between, let's see, actually I want to turn off the, there we go. The difference between intramolecular versus intermolecular forces. The graphic below is showing the labeled difference between intra versus inter. Intra is going to be between atoms within a molecule, so the covalent bond between hydrogen and chlorine, that's an intramolecular. They're sharing electrons, and that's held within the molecule. So that's a relatively strong force. The intermolecular is the attractive force between neighboring molecules, where you have a partial negative on the chlorine attracting a partial positive on the hydrogen. This is not a formal bond. It is just an attractive force. So they're partial charges, very weak forces, but they are going to hold molecules together. And that's where we see differences in solid, liquids, and gases, the strength of this attractive intermolecular force. So given the question or presented, are you able to explain the difference between these two? And here's just a quick description of both of them. To do a quick follow-up on intramolecular forces, because last week we're talking about chemical bonding, so looking at just singular pure substances where you have looking at the molecule, the structure, drawing Lewis structures. We're going to refresh ourselves on the type of intramolecular forces, and then intermolecular forces. When we start attracting multiple molecules, that brings up a larger, broad conversation that we'll get into later. So the main types of bonding that we were getting into in Unit 2 were ionic bonding, covalent bonding, and metallic. Metallic is a type of covalent bonding where electrons are being shared, but it's over these delocalized electron fields where the metal atom is treated as kind of a positive center, and the valence electrons for each atom are shared amongst all the metal atoms, which is why metals conduct electricity really well. Anytime there's a medium where electrons can move, then that creates the possibility of conductivity. The covalent bond, so the molecule is a discrete structure. It's not this continuous array like metals can be or ionic compounds can be, where you just get these repeating patterns over and over again. The covalent molecule is a discrete molecule, and that's going to be isolated within their own electron cloud. We'll get into solids a little bit more with crystal structures in a second. So, how would you complete this statement? The following molecules have a what kind of force as a result of the asymmetrical arrangement of electrons? Anytime you have an uneven arrangement of electrons or a lopsided molecule, that follows the word asymmetrical, and that generally yields dipole forces or a dipole moment. So all of them are going to have a dipole moment in the direction of the largest electronegative atom, or the most lopsided side. So oxygen is the most electronegative, And so the dipole will be towards the oxygen. That is going to be the most partial negative side, and the opposite of that should be the most partial positive side. And this is going to have an attractive force with neighboring dipole molecules, kind of like how magnets have their opposite poles and they attract each other that way. These are going to have opposite electrostatic properties, kind of like a proton and electron attract each other. They have a positive negative attraction to each other. So there's several different models we can use to show the differences in polarity or the lopsidedness of molecules. And so when we're looking at Lewis structures are a good way of just showing the structure, but don't always show the best type of geometry, because you can draw the Lewis structure in a way that they look linear, where in reality this is not a 180 bond. This is actually a 120-degree bond based on Vesper theory. Do that so you can actually see it. So one of the tricks with Lewis structures is using Vesper theory to look at number of domains and bond angles, which isn't necessarily going to look how it's going to be drawn. We have space filling models, which are usually seen on online programs. We have the PhET simulations that use these kind of models as well. The polarity simulation on PhET does a really good job of showing these space filling models and dipole moment. So I'm going to attach that link to the polarity PhET simulation after this as something you can use to review. Okay, so to talk about polarity, this will occur when you have a discrete molecule. Usually we're talking about covalent molecules when we talk about intermolecular forces. So a molecule like water has an unequal or an asymmetrical arrangement. If we're looking at the Lewis structure of water, you do have to be careful. We talked about this a little bit last time. If you have HOH and you're drawing it like this looks linear, it looks symmetrical, where both sides are the same. But in reality, it is a bent structure. The tetrahedral is going to have theoretically 109.5 degree angles between bonds. And the actual bond angle is a little bit closer to 104.5 degrees. So it's not a linear bond, it is a bent structure. And this bent structure is going to create a lopsidedness where one side is going to be partially more negative and the other side is going to be partially positive. So the molecular geometry section we just did is going to have a huge relevance into your ability to predict polarity or predict which side, if it's going to be bent or perfectly symmetrical. The word discrete in science and chemistry is talking about an individual isolated molecule, not some sort of continuous array like we would get with ionic, where you get positive, negative, positive, negative, positive, negative. It just keeps on going and going and going forever. With covalent molecules, we have here's a molecule, and this is going to have its own polarity, and that is going to be its own discrete molecule. And that can be near another covalent molecule, which has its own polarity, and that's a second discrete molecule. And that's how we're using the word discrete in this case. And we really only use it with covalent or molecular structures. So the visual below is just showing colored electron density, where red is the lack of electron density, and the blue is where there's a greater electron density, meaning at any given time there's going to be more more electrons on the blue side compared to the red side. And when that happens, when there's an unequal sharing of electrons or positioning of electrons in a molecule, we call those polar, or there's a dipole in that molecule. And those molecules, if you have multiple molecules near each other with dipoles, they're going to have an attractive repulsive forces according to Coulomb's law, where opposite charges are going to attract each other. If they're really close to each other, the attractive forces are felt more. Stronger separation of charges, stronger dipoles will generally attract each other more. Whether that separation of charge comes from London forces or dipoles. Now, all these intermolecular forces that we're going to be talking about are generally weak compared to full charges, which we see in ionic compounds like sodium chloride. That's why we're calling them partial charges. To give a rough number, the intermolecular forces between hydrogen bonding, or molecules that are exhibiting hydrogen bonding, that's still only 15% of the strength that we would see in some of the covalent networks like diamond or ionic structures, or just a covalent bond in general. So when we're looking at Lewis structures or the elements involved in these compounds, we're able to make statements like one element is more electronegative than another element based on its location on the periodic table. And we had a section like that previously where we're looking at the periodic table, and we know the top right corner are the most electronegative elements, specifically fluorine. Fluorine is the most electronegative. It is the smallest atom in period 2 that still has the desire for an additional electron. It has 7 out of 8 on its valence shell. We know neon, yes, it's smaller, but it has a full shell, so it doesn't really have an electronegativity value. In fact, the first couple noble gases do not have electronegativity values. They're inert. They don't want to react. So fluorine is the most electronegative. Its size allows its nucleus to be really close to neighboring electrons, which that distance creates a higher level of attraction. And also the fact that it only needs one more electron to fill its valence shell. There's multiple concepts that build into this idea of electronegativity. So the more electronegative element between two that are bonding will have the greater electron density. And that's where we can draw the dipole arrows. The arrow goes towards the more electronegative side, and you put a little plus on the side that's slightly more positive. So that's a dipole arrow. When there is a large or significant separation in electronegativity, we call these polar covalent bonds. So that's generally anything that has a greater than 0.5 difference in electronegativity. And there's charts that can give you electronegativity values, but generally 0.5 or greater will yield a polar covalent bond. And then anything greater than about a 1.7, anything greater than about a 1.7 difference in electronegativity, that's where you get to ionic. So the difference between covalent and ionic is just the separation of electronegativity. You have metals that have a really low electronegativity value, and when they come into contact with nonmetals with a really high electronegativity value, that difference in electronegativity is enough to be an ionic bond where there's transferring electrons instead of just sharing electrons. Anything less than 0.5, yes, there could be a slight difference in electronegativity, but it's not enough to really be considered polar. So carbon-hydrogen bonds are probably the most popular one that are non-polar. They're pretty close in electronegativity, and that's just a type of bond that we're not really going to consider for polarity, even though there is like a 0.4, 0.3, 0.4 difference in electronegativity. Carbon-hydrogen bonds are very popular. If we add all these dipole arrows up between specific covalent bonds within a molecule, we can add all these dipole vectors together and get an overall dipole moment. And I have some examples of that in just a second. The dipole moment is the main one we look for when we're talking about the direction of polarity. I don't know how much of these dipole moments you actually have to draw on the AP test, but you may just need to know the concept of an overall net dipole in reference to which side of the entire molecule is more negative and which side of the entire molecule is slightly more positive. So, types of intermolecular forces. Hydrogen bonding is a dipole-dipole force that is the strongest. It's the strongest dipole-dipole force. So it is a polarity, attraction of polarity, specifically when a molecule has a hydrogen attached to a nitrogen, oxygen, or fluorine. And that is unique in that nitrogen, oxygen, and fluorine are second period elements, so they're really small, and they're very electronegative. So that's going to create a significant separation in polarity over a small space. So that partial positive charge on the hydrogen is enough to create an extra strong attractive force to those partially negative oxygen, nitrogen, or fluorine. We see this especially in water, and the depiction on the right is two water molecules near each other, creating this hydrogen bond. We have ethanol, which has an OH group, and the hydrogen on the ethanol is attracted to the oxygen of the neighboring molecule. So that's a hydrogen bonding. The hydrogen is attracted to the oxygen in that case. And then there's also the rare possibility, I don't really think we need to focus on this one too much or remember, but within a molecule itself, if it's large enough, you might have hydrogen bonding between atoms within a molecule on separate branches of the organic structure. Fun little thing that pops up every once in a while. We do have a situation where we might be looking at organic structures, larger hydrocarbon structures. Even though we're not doing organic chem in this class, just being able to recognize where hydrogen bonding may occur is important. So this PowerPoint is sometimes feels like a glorified Google image search. We have different representations here where they're showing the correct geometry. We're not looking at lone pairs are not shown. So whenever you have like this asymmetrical structure like in ammonia, the lone pairs are pushing all those other bonds closer together. So because methane is perfectly symmetrical, all the hydrocarbon bonds are equally positioned away from each other. This has a dipole moment of 0, which is considered non-polar. So we use this word non-polar to talk about symmetrical molecules where everything is equally distributed. And you can see another couple examples of non-polar structures where the dipole moment between is 0, even though the individual carbon-oxygen bond shown in carbon dioxide, that is a polar covalent bond. There is a significant difference in electronegativity between carbon and oxygen, but the symmetry of the molecule cancels that out. So we say the overall molecule is nonpolar. Even triangles can cancel each other out. We haven't done a whole lot of vector geometry. You might have done that when you're getting into calculus, but the geometry of a triangle is that even though they're 120 from each other, those are all in the same plane. And so the 120 angles within the same plane will cancel each other out as well. So trigonal planars, which is shown by the last one, are also going to be non-polar as long as all the attached terminal atoms are the same. If any of these, let's say this oxygen was a fluorine instead, then even though it's looks symmetrical, it's a trigonal planar, if one side is more electronegative than the other, there would be a difference in dipole, and so that would have a polarity towards the fluorine in SO, if this was SO2F, for example. That's no longer symmetrical. So, types of forces. These are ones that happen with covalent structures. The ion dipole is included at the end for when ionic structures dissolve, ionic salts dissolve in water. We have dispersion forces, which are exhibited in all compounds, all molecules that have have electrons. There's just this random situation where temporarily there's more electrons on one side than the other, and that creates a temporary dipole. The larger the molecule, the more electrons. The larger the molecule, is a greater sloshing effect of the electrons, greater separation of distance between where these electrons are located. So larger molecules are going to have stronger dispersion forces. With the dipole forces, it's just a polar molecule, lopsided. And then we have the hydrogen bonding, which is a very specific type of dipole forces, and the conditions are given there. When ions, ions dissolve generally in water, because water is the universal solvent, we can see an example of a positive ion center attracting the partial charges of the water molecules. This isn't hydrogen bonding because the ion center doesn't have the components of hydrogen bonding, but it is a dipole attractive force to the charged ions that have dissolved. And this is the main reason why ions will dissolve readily. Most salts will dissolve in water because the strong dipoles of the water molecule will be separating the positive and negative charges, and they'll go their own separate way, and the water molecules will surround each of the charged ions. Just some things that happen. I wanted to show this because we don't always talk about pure sources. We're not always talking about just methanol attracted to methanol or water attracted to water. You can have heterogeneous mixtures where there still is an attractive force you need to identify. So ion dipole is a heterogeneous mixture. Types of salts with water. Methanol and water can still have hydrogen bonding if both of the molecules, even though they are different, still have the necessary bonds for hydrogen bonding. Here we see methanol, the top right example. Methanol with chloroform. One of them has the structure for hydrogen bonding, but because chloroform does not, we're not going to consider it hydrogen bonding unless both of them satisfy the hydrogen bonding requirements. So this would just be a dipole-dipole interaction. Another rare thing that you might have to address is when you have a polar molecule, looking at the bottom middle example, a polar molecule next to a nonpolar molecule. So we have polar with nonpolar. Generally, these don't mix. We learned that if we mix these two together, they don't dissolve each other very well. But what can happen, because we know that nonpolar are governed by London dispersion forces, and London dispersion forces are temporary charges, temporary dipoles. If you get this next to a polar molecule that has this partial negative, partial positive side, it can actually help induce that temporary dipole a little bit. So the partial negative side of the acetone might pull some or push some electrons to the other side of the C6H11 side, so that the side nearest the partial negative of the acetone, this side is slightly partial negative, then it'll induce the dipole on the C6H14 molecule to be opposites attract. So like pull the electrons to one side or the other based on which side is near the polar end of the acetone. That's called an induced dipole. Get a polar molecule near a nonpolar molecule, the polar molecule will force the electron positioning of the other nearby substance. And we see this in MRIs. The magnetic resonance imaging the machine that is used in hospitals actually polarizes or uses the polarity of water, and it will induce the direction of all the water molecules to align based on all the magnetic the induced magnetism of the machine will align all the water molecules and force them all in one direction. And that is similar to kind of what happens when a polar molecule gets near a nonpolar molecule. It can force the electrons in a particular position. Obviously, I'm not a medical tech, and I don't know the finer details of an MRI, but I try. So one of the things we can do is look at a structure and determine which type of intermolecular forces at play. This is a graphic that I plucked that basically is a table that shows looking at a structure and discerning what kind of forces of attraction are between them. So let's look at this one more time. So if it's symmetrical, then that puts into one side of the graph. Symmetrical is going to be relatively nonpolar. Then methanol has the OH bond, making it hydrogen bonding. And if there's no hydrogen bonding, then it's going to be the dipole forces. And you can see differences in boiling point as a result of the polar structure has a higher boiling point than the nonpolar structure. And you can generally make this connection when they're relatively similar in size. So this is a GIF. You can, when you look at the PowerPoint, you can watch this GIF all the way through. There's tons of different tables that show how to differentiate between the types of forces, some flow charts. One of the first questions we can ask is, are ions present? Yes or no? If it's no, then we can say within that molecule, that's usually where we're at, a covalent molecule, is it polar? And if it's not polar, then we get dispersion forces. If it is polar, if the covalent molecule is polar, then we are looking at whether it's dipole-dipole or the more advanced version of dipole, which is hydrogen bonding. If ions are present, is it a heterogeneous mixture with polar molecules like water? So this is where we have the dissolved state if we have ions in water. If it is a homogeneous source of ions, or they're just ion-ion, then that's where we get ionic bonding. So I found this flowchart and I thought it was pretty relevant, even though it's packed with some information. You got some examples, and then on the bottom it shows increasing strength. Quick thing about van der Waals forces, this is a older term that's really no longer used. So if you start hearing or reading about van der Waals forces when you're looking up videos or doing your studying, we don't really use van der Waals forces anymore. It's either dispersion forces, dipole, or hydrogen bonding. So we'll stick to that. So relative hierarchy of strength, the hydrogen bonding, dipole-dipole, London dispersion forces are about 15% of the strength of ion-ion or covalent bonding. So it's intermolecular forces are relatively weak when you compare them to ionic bonding or covalent bonding. So I'm going to pause for a second for some questions, and we're going to get into the types, the ways that intermolecular forces and the attractive forces manifest, and how do we compare and measure them. So what we're going to do next is use the physical state of a substance to make predictions about if substance A has stronger attractive forces than substance B. So generally, really strong attractive forces manifest as solid state because those atoms or molecules are held together really, really tight. We're assuming constant temperature amongst all those example substances. Then we have a liquid, which is kind of in the middle. Liquids are actually pretty rare in nature. We see water, we see things dissolved in water, maybe some alcohols, but other than that, there's not a whole lot of naturally occurring liquids at standard temperatures. And then gases are also really common for substances or molecules that are held together weakly. So the picture on the left is chlorine gas. The chlorine atoms are held together by, or the chlorine molecules are held together by London dispersion forces, which are weak compared to the strength between bromine atoms, which is why we see bromine as a liquid. And even further down, iodine is a solid. So you can see just within the halogen groups, those diatomic molecules in the halogen group, it goes from gas to liquid to solid as we go further and further down, as London dispersion forces are more and more influential. The solid state is a particular one of interest. We have two different types of solids. We have crystalline solids and we have amorphous solids. The crystalline solid is by far the most common that we'll be talking about. They're this repeating pattern, this array of positive and negative charges or atomic structures or covalent structures. It's just, crystal can be used for anything in the solid state where its pattern repeats itself. It's not solely ionic compounds that are crystals. You have water crystals. Ice is a water crystal. Amorphous solids like glass or plastics are solids, but there's not a repeating pattern. They're disorganized, and usually over time that structure starts falling apart because there isn't that solid, or there isn't that constant repeating array that is sometimes more stable. Usually high heats will break down these glass and plastics without fully melting them down. That's why you don't really want to heat up plastics, because they'll like get some partial separation and they can get in your food. There are some tables that are pretty common to look at that differentiate the types of solids. So when you see molecular solids, when you see metallic solids, ionic solids, or covalent networks, we're going to assume all these are talking about crystals, by the way. So these are all different types of crystals formed by molecules, metals, ions, or a covalent network, which is in diamond. Another picture of diamond we'll see in just a moment. You do need to know how to differentiate between these types of solids based on some of their properties and how they're held together. Molecules, covalent molecules, those are held together by intermolecular forces. So all that talk about intermolecular forces was specifically for molecules. And those are generally seen as the weakest, which is why we see a lot of those in gases and liquids. Metals have a wide range of melting points and boiling points, depending on the atom. We see some liquid metals like mercury. We see some metals that are really close to liquefying. Gallium liquefies, and if you stick it in a bag and stick it in your mouth so it doesn't get all over you, gallium will melt at between room temperature and about like 60, 80 degrees. And here's a quick description of metals again. And then ions, higher in strength, ionic bonding, and we talked about how to differentiate between lattice energies of ions based on size, based on charge in the last section. And then the strongest is going to be a covalent network. So there's really no break in the molecule. It just keeps on going and going and going and going. And this is what diamonds exhibit. Until you cut the molecule, the carbon just keep on repeating itself over and over and over again. Quick second, I'm going to. So another use of these tables is to differentiate these types of solids based on melting point, hardness, brittleness, which is their texture, and then the conductivity. So a very viable question is, you're given a description of a solid on one of these categories or more, one or more of these categories, and you have to justify your choice of what type of solid it is: molecular, ionic, metallic, covalent network. One of the common ways to differentiate is by their conductivity. Generally, molecular solids don't conduct. Water, pure water, is a non-conductor. Pure metals in their solid state do conduct. Ionic compounds do not conduct electricity unless they're dissolved in water. So the ionic solid does not conduct electricity. So if we're trying to differentiate between types of solids based on conductivity, a positive test is if it conducts in the solid state, it is most likely a metal. So that narrows it down to one choice right away. And you get a little bit of hardness and brittleness, which you can take a look at. Generally, the weaker held structures are pretty brittle, and as you get stronger and stronger forces, they're more and more well held together, so the hardness is larger. And then melting point is a direct measurement of strength. So the stronger the solid, the higher the melting point. And by stronger, I mean the like lattice energy, how much energy it's going to take to break down that solid structure. So these would be good tables to review. I just wanted to show some general melting points of common structures, compounds. Neon being a pure gas at room temperature, really low melting point. We know that the coldest temperature possible is -273. So you're not even going to see neon turn into a liquid or a solid until it gets really close to absolute zero. And hydrogen and helium are even lower. And then as you look at this table, you can start differentiating and justifying some of the differences in melting and boiling points based on what kind of atom or structure it is. Metals generally are hard to do that. Pure metals, there's a wide range in melting and boiling points with pure metals. So melting point and boiling point isn't really a good indicator for whether it's a metal versus some of the other ones. The ones that are predictable are really low melting and boiling points for covalent molecules, and really high melting and boiling points for ionics or covalent networks. So we'll use the extremes to help justify what type of solid it is, whether it's a covalent at the low melting point, boiling point extreme, or the ionic or covalent network at the high melting boiling point extremes. So to get a little bit into crystals, we don't have to know the names of all these unit cells. There's a whole separate part of that that's, I think, is pretty interesting. But we just have to know the idea of a repeating pattern, which is the unit cell. If that pattern repeats itself over and over again, you get the entire lattice structure. And then you can use these space filling models to represent the size of the electron cloud for each atom, and the fact that there are little gaps that exist between atoms because they're spherical. When we stack spheres on each other, there's going to be gaps in between these spheres. So whether these structures are filled by a homogeneous atom, all the same atom like in metals, or an ionic structure where the charges are alternating, they're all spherical and they're going to arrange themselves like spheres do. We have the possibility where they just stack on top of each other in an open arrangement where there's the large spacing between molecules. This is a simple arrangement. And then we have this close packing arrangement where the spheres actually alternate rows where they're filling the gaps in between. So just imagine you're throwing a ton of marbles into a jar. Marbles don't sit perfectly on top of each other. They sit offside to one another to fill the gaps in between these spheres. This is important when we're talking about alloys or types of alloys. We have pure metals, which all atoms are the same. Then we have substitutional alloys where if you have a metallic array, but you have different elements of metals, as long as those metals are around the same size, you can take one metal out and replace it with another metal about the same size. You're really not going to change the crystal array too much. So substitutional is where they're about the same size. And you can just use the location on the periodic table to justify that. If you have an atom that's blending with another metal and you have to melt it down, allow it to resolidify so the atoms intermingle and resolidify within its own lattice structure. Interstitial alloys occur when they're resolidifying. There's really tiny atoms filling the gaps in between larger atoms. So an interstitial alloy, one atom is much larger than another. And we talk about alloys being multiple metals together, but often one that's referred or talked about with interstitial is steel, where the really small carbon atoms are filling the gaps in between the iron atoms. And the more carbon atoms you have in steel, the stronger it is, but the more brittle, the more likely that steel is going to break. Less carbon makes it a little bit more flexible, that our atoms can shift around each other, a little bit more flexible, but more susceptible to deforming. And there's a possibility of having alloys with a lot of different elements and getting both substitutional and interstitial. But you should know the difference between substitutional and interstitial alloys. There's been questions where they give you data on the size of atoms, and if they're relatively close, then you can say it's a substitutional alloy, most likely. Other types of crystals. These are allotropes of carbon, and so on the left we have diamond, which is an ongoing covalent network. Each carbon can bond to 4 other carbons, so we have this tetrahedral array, and it really doesn't stop until you cut the diamond. That is one of the strongest structures that we discuss. There's earth science, you talk about a hardness scale, and that's a 10, that's the highest on hardness scale. Graphite is what we write with in our pencils, and these are layers and layers and layers. Each layer itself are sp2 carbons in graphite, and so they have their delocalized p orbitals that share above and below, and that is why graphite can conduct electricity. This is one of the rare occurrences where a network solid, covalent network solid, can conduct electricity. Each of those layers are held to each other by London dispersion forces. And so we see graphite as a solid, of course, but when you write, the shaving off of the layers, the graphite comes off the pencil really easily because all those layers are held together just by London dispersion forces. So graphite does conduct electricity, whereas diamond does not. And that's mainly because of the sp2 carbons versus the sp3 carbons in diamond. So you should be able to justify differences in diamond versus graphite in respect to hybridization and why you can write with graphite and not diamond. So we've gone through a deal with solids, different types of solids. Phase diagrams aren't really going to be assessed on the AP test according to what the College Board has released, but knowing the differences between phases, these diagrams are helpful in showing different pressures and temperature ranges. Generally, gases prefer larger temperatures and lower pressures so they can spread out, and that high temperature is going to allow them to move around really rapidly. And generally solids are seen at low temperatures and higher pressures. Higher pressures meaning forces that are pushing the molecules closer together, they're more likely to be in the solid phase. This phase diagram is a generic phase diagram. This is not for water. Water, if I were to draw that in red, would deviate from the triple point more to the left. That would be what water would look like. And that's specifically because the most dense state for the water, or sorry, the least dense state for the water as you go to less and less pressures, the least dense state is a gas. And as you increase the pressure more and more, it changes to a solid and then back to a liquid at the highest point. Liquid is the most dense state for a solid. Whereas ice is less dense, and that's why ice floats. And you can look at phase diagrams to help justify why ice floats for water. However, this particular one is just a generic phase diagram. A further look at this phase diagram, there's a lot of points we can identify. We can talk about the triple point, where all three phases are present or exist at the same time. There is a specific temperature pressure range for all substances where the triple point occurs. Just a lot of them aren't very common, especially at room or normal pressure. There are very few triple points at room pressure. There is this critical point where the phases start blending together. So point C on this graph in particular is where at some point at high enough temperatures and pressures, the phases between liquid and gas kind of blend together. So you get this gas that can dissolve substances really well. And this is actually used in a lot of production. Supercritical carbon dioxide, so this really high temperature carbon dioxide is used to create decaffeinated coffee to help extract certain chemicals like the caffeine. So the caffeine would dissolve in this supercritical carbon dioxide and then separate it out from the substance from the source. So boiling point and melting point is really commonly used to justify differences in strength. And the stronger atoms or molecules are held together, generally we see a higher boiling point and melting point. Direct correlation of strength. So we see phase changes between solid to liquid, liquid to gas at specific temperatures based on how much energy is required to get the solid to break down to a liquid, and then even higher temperatures to get the liquid to completely separate into the gas state. So using melting point or boiling point to justify differences in strength is an extremely useful tool, since our test is going to be largely about providing justifications for patterns or trends that you're noticing from data or graphs. So let's try this. So looking at this graph, this is a difference in boiling point for common structures with bonds to hydrogen. So we're changing the element and it's bonded to hydrogen. So you can see oxygen bonded to hydrogen, compounds where fluorine bonded to hydrogen, so on and so forth with nitrogen bonded to hydrogen. And you should be able to justify differences in boiling point based on where the atom is located on the periodic table, where the element is. and understanding the properties of the difference in hydrogen bonding. Even though fluorine is more electronegative than oxygen, we see a stronger attractive force between water molecules in each other than HF molecules in each other. So why could that be? What else is there? What other thing to consider besides just electronegativity? And then the trends with the other molecules, period 2, 3, and 4, follow a general linear pattern. Between periods 3, 4, and 5, it's not as much a polarity thing anymore that's considered as far as differences in electronegativity. As you go down the periodic table, periods 3, 4, and 5, it's more about just which atoms are larger, which ones have more electrons. So the more significant force at that point is London dispersion forces. Whereas in period 2, we're largely worried about differences in electronegativity, polarity, hydrogen bonding. So I'm going to pause for just a moment, and you can think about differences or justify the difference between water and hydrogen fluoride. So when we're looking at the period 2 elements and their ability to hydrogen bond, it helps to look at the Lewis structure. Water has optimal hydrogen bonding because it has 2 hydrogens and 2 lone pairs. So the ratio of lone pairs to hydrogen is 2 to 2. Where with HF and NH3, there's really only a possibility for 1 hydrogen bonding to occur between molecules. 1 hydrogen, 1 lone pair. And with HF, there's 3 lone pairs, but there's only 1 hydrogen. So still only 1 hydrogen bonding happening between molecules in this 1 to 3 ratio or the 3 to 1 ratio. There's really only 1 hydrogen bonding occurring between HF and NH3. Where with water molecules, there's 2 different sites for hydrogen bonding. And that is got essentially twice as much hydrogen bonding with water molecules compared to the other 2. More hydrogen bonding, stronger attractive forces. Water is an extremely unique molecule. That's why 70% of our body is made of water. Body mass. Let me know, chat, if you need a better explanation of that. Here's another graph that includes the carbon group in this graph. You can notice that adding the carbon group to this graph, there's a significant difference in the period 2 elements. In fact, the carbon group follows the most linear trend out of all of them. There really isn't any oddity with methane, CH4, because there's no hydrogen bonding going on in methane. CH4 follows nonpolar structures. In fact, all of the purple ones are nonpolar, which is why they're the lowest on the group. And they're going to have less electrons than the elements in group 5, 6, and 7. We did have a quick question, so let me try and draw my Lewis structure a little bit better. So HF has, the fluorine has 3 lone pairs, but there's only 1 hydrogen. So if I were to draw HF next to another HF, there's still only 1 hydrogen bond occurring between these molecules. If I were to do the same with ammonia molecules near each other, there's still only 1 possible hydrogen bonding because the hydrogen is only attracted by the lone pairs. There has to be lone pairs on the nitrogen to attract the hydrogen from neighboring molecules. So there's only 1 site for hydrogen bonding with both of those examples. When you have water, you can probably see where this is going. There 1 hydrogen with 1 lone pair and another hydrogen with the other lone pair. So water in particular has 2 sites for hydrogen bonding, where most every other molecule will only have 1 viable site for hydrogen bonding. And we're able to make this comparison when all these molecules are about the same size. Thanks for asking the question. It gives me a chance to elaborate. So reading graphs and justifying differences in the graphs is going to be important, or data given. Usually you're not going to have to remember every single detail from scratch. You'll be given some boiling points, you'll be given graphs, and so you're going to be able to justify which one has the higher boiling point with the use of all these intermolecular force concepts and things that we discussed today. So you're not going to be doing all this from scratch, but based on some presented trends or presented data, what intermolecular force, type of attraction, size, temporary dipole, which factor is the most influential to justify some presented data. So I'll give you some example questions this week to look at, and also some videos to help speed us along. There are some concepts that we've gone over, of course, but I want you to review those on your own, because I'm going to be picking the longer sections like intermolecular forces that I wanted to lecture on personally. There are some properties of liquids like viscosity, surface tension, that there's going to be great videos on. Properties of gases like vapor pressure, PV-nRT, which is PV-nRT has been embedded in a lot of our AP review anyway, so we've been getting a lot of PV-nRT questions. Those are ones that I'll provide separate videos for that you'll review on your own time. The College Board has this information as well. And then you can use those to answer some questions that I'm going to be posting. If you have further questions about these things, drop into my office hours. You can always schedule with me outside of office hours if you want to pop in and ask questions live, if this helps, or you can just email me questions. I can write you back a email response. Other than that, our next meeting will be on Wednesday, and thanks for stopping by. If you have questions, you can hang out and chat.